Exponential functions. Our learning goal today is to explore exponential functions and compare them to quadratic functions. Please ensure you have the lesson printout so you can follow along with this video. Let's practice evaluating each power. 2 to the power of 3. As you recall, this just means 2 times 2 times 2, where the 2 is the base and the exponent tells us how many times we have to multiply it. To evaluate this, we're just going to multiply across. 2 times 2 we know is 4, and then we'll bring down this 2 over here. 4 times 2 we know is 8. 2 to the power of negative 3. We can see we're dealing with a negative exponent, and there's a special rule that we need to take into consideration when evaluating this. So the way we evaluate a negative exponent is we take the reciprocal of the base. Since 2, or in other words 2 over 1, is our base, we must take the reciprocal of this, which is 1 over 2, and then we cube it. So once we take the reciprocal, we lose the negative sign on the exponent, and now we can evaluate this new number. And if we do that, we expand that, we'll have 1 over 2 times 1 over 2 times 1 over 2. And if we evaluate that, we just multiply straight across on the top, 1 times 1 times 1, which is 1, then 2 times 2, which is 4, times 2, which is 8. So our answer for this is 1 over 8. So the rule for this is as follows. And I'll write that out formally for you right over here. And move it over here so you can see it. Shrink it down for you. So the rule is, step 1, we're going to write the reciprocal of the integer. For example, the integer of 2 is 1 over 2. There's a reciprocal. And then the negative exponent becomes a positive exponent, and then we just evaluate it. Let's try some more examples. Let's look at this one here. 3 to the power of 0. If you recall, anything to the power of 0 is just equal to 1. Let's try this one here. Negative 3 to the exponent 4. What this means is that our negative's on the outside, and because there's no bracket around it, we're only considering the 4 as being the one with the exponent. Or sorry, the 3 is being the one with the exponent. So we have something like this, and then we're just going to multiply across. So 3 times 3, we'll leave the negative sign in front. So 3 times 3 we know is 9, times 3 times 3. 9 times 3, that's 27, times 3, we'll leave the negative sign in front. And 27 times 3 is going to be equal to 81. So our final answer for this one is negative 81. Let's try the next example. We have negative 1/2 to the power of negative 4. As you can see, the exponent is negative, so we must follow the rule mentioned earlier. We must take the reciprocal of the base and change the negative exponent to a positive exponent. So what is the reciprocal of negative 1 over 2? Well, it's negative 2 over 1. Or, in other words, just negative 2. And then we change the negative 4 to a positive 4. And then we can expand this. So this is the same thing as negative 2 times negative 2 times negative 2 times negative 2. And if we multiply across, negative 2 times negative 2, that's positive 4. And then we still have these two negative 2 to deal with. So 4 times negative 2, that's going to be equal to negative 8. And we still have one more negative 2 to deal with. 8 times negative 2, well, that's positive 16. So our final answer here is positive 16. Just to note, we're not taking the negative reciprocal, it's just a reciprocal. So because it's negative 1/2, it's just going to stay negative, but 2 over 1. So we flip it there. Don't take the negative reciprocal. So be careful with that. Here we have negative 9 to the power of 4 divided by negative 9 to the power of 2. Because we have like bases and different exponents, we can use the exponent laws. When dividing, we can subtract exponents. So this would be equal to negative 9 to the power of 2. And expanding that, we would have negative 9 times negative 9, which is equal to positive 81. Let's try one more example. Here we have negative 4 to the power of 2 divided by negative 4 to the power of 5. Using the same exponent rules that we used before, we can subtract these exponents. This will leave us with a negative 4 to the power of negative 3. We can evaluate this now using our new exponent rule for negative exponents. We're going to take the reciprocal of the base. So in this case, this is negative 4 over 1. So the reciprocal would be negative 1 over 4. And then we take the exponent, but instead of being negative, we now make it positive. And now we can evaluate. So expanded, this would look like this. Negative 1 over 4 times negative 1 over 4 times negative 1 over 4. And we can go ahead and evaluate that. If we multiply, let's do this, the first two brackets are negative 1 times negative 1. That's negative 1. And 4 times 4, we know that's positive 16. Oh, sorry. Negative 1 times negative 1 is positive 1. So it's 1 over 16. And then times negative 1 over 4. So 1 times negative 1 is going to be negative 1. And then 16 times 4, that's going to be 64. So our final answer here is going to be negative 1 over 64. Quadratic functions versus exponential functions. Quadratic function is a function where the lowest or highest degree within its terms is 2. In other words, squared. We've seen many examples of these so far in this unit. Y is equal to ax squared plus bx plus c is the standard form. Some examples include y is equal to 2x squared plus 3x plus 10, or y is equal to 4x squared, or y is equal to 3 times x minus 2 times x plus 4. And if we expanded that, you would get a degree that is squared. Exponential functions. The general exponential function is y is equal to a to the power of x, where a is any value greater than 0, and the variable is the exponent. Some examples of exponential functions include y is equal to 2 to the power of x, y is equal to 10 to the power of x, and we're going to be replacing the x with our different values for x. So let's see how the graphs of quadratic functions compare with those of exponential functions. Complete each of the following tables of values. Plot the points for both graphs on the grid provided. So let's start off with the most basic version of a quadratic. Y is equal to x squared. If you plug in the x value here, our equation would look like this. Y is equal to negative 3 squared. And negative 3 times negative 3, well, that's just positive 9. Negative 2 squared, that's 4. Negative 1 squared, that's 1. 0 squared, that's 0. 1 squared, that's 1. 2 squared is 4. And 3 squared is 9. So let's plot these points on our grid. To help us out, in this case, I'll write the numbers on our grid. So you have 1, 2, 3, 4, 5, 6, 7, 8, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, 1, 2, 3, 4, 5, 6, 7, 8, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and negative 8. So let's go ahead and plot our first points, and I'm just going to change colors for you so you can see it a little bit more clearly against the dark colors of the grid. So our first point is negative 3, comma 9, so it's just one above here. The next point is going to be negative 2, comma 4, then negative 1, comma 1, then 0, comma 0, 1, comma 1, 2, comma 4, 3, 9. And here we see the familiar shape of a parabola. Now, let's take a look at this exponential function. Y is equal to 2 to the power of x. To evaluate this, we're going to plug in these values of x into this equation. So our first would look like this. Y is equal to 2 to the power of negative 3. And as we said, this would be equal to y is equal to 1 over 2 to the power of 3. And if we expanded that out, we'd get 1 over 8. The next one is in a similar fashion. So 2 to the power of negative 2. So replacing the x value with negative 2 here, and we would get y is equal to 1 over 2 to the power of 2. And if we expanded that and multiplied through, we get 1 over 4. Following this pattern, we'd get 1/2 if you kept on plugging in the values for x into here. 0, we'd get 1. Anything to the power of 0 is 1. 1, we'd get 2. 2, we would get 4. And 3, we would get 8. Now I'll change colors here so we can graph it on our, let's use a nice baby blue here. So let's graph these points on our same table of values. So if we do 1 divided by 8, we would get a number that's probably easier to graph. So 1 divided by 8 is equal to 1.25. So if you turn this to a decimal, it's going to be equal to 0.125. And so we would imagine where that would be. So let's zoom in here. So it'd be negative 3 and positive 0.125. So it's going to be right over here. Very difficult to draw because it's such a small number. At negative 2, we have 1/4 or 0.25. So a quarter of the way. So it's a little bit higher. You can see it's not much higher. Very close. Then we have at negative 1, we have 1/2 or 0.5. I'm just turning these into decimals. So negative 1, we get 0.5. At 1, we have, at 0, we have 1. Anything to the power of 0 is 1. And at 1, we have 2. And at 2, we have 4. We have a common point there between the two. And then at 8, with 3, we have 8. So 3, we have 8. And we can get a curve that looks like this. And there's some unique properties to this curve. And we'll discuss that in just a second here. Let me draw that a little bit better for you. There we go. So you can see the curve looks different from the quadratic. The quadratic is symmetrical, while the exponential is not. Let's switch over to Desmos to look at one cool feature of the exponential function. So here we are in Desmos, and we're going to graph that same exponential equation. So y is equal to 2 to the power of x. So there's our function. And you can see it looks very similar to the one that we drew by hand. And what's interesting is if we zoom in on these x values here, we can see as we get bigger and bigger, it gets closer and closer to the x-axis, but it'll never touch it. So as we go farther and farther out with bigger negative x values, you'd expect it to get to the 0, but in fact, it'll never touch it. And there's a special name for this type of relationship. We call this an asymptote. So as you can imagine, if we continued on with this line here, it'll get closer and closer to 0, but it'll never touch the x-axis. And we call this, as it approaches a number but never touches it, an asymptote. So it's an asymptote. When you get to grade 11, we'll be dealing more with asymptotes, as well as in grade 12. Let's summarize everything we've learned about exponential functions. The equation is in the form y is equal to 2 to the power of x. This is just an example. The base could be anything. The graph of it would look like this. And it grows in a way we call exponential growth. You can see it getting bigger and bigger. And the table of values will just say refer to the one above. And the key features are the horizontal asymptotes. So it approaches but never touches a value. In this case, it approaches the y value is equal to 0, but it'll never actually touch the y value is equal to 0. And in this case, as I said, it's y is equal to 0. So let's answer some more questions. Are exponential graphs symmetrical? No. Will the exponential graph have a y-intercept? No. It'll never touch y is equal to 0. As x increases, y increases exponentially. So just getting bigger and bigger. And as x increases, in the negative direction, the y values decrease towards 0, but never reaches 0. And y is equal to 0 is the equation of the horizontal asymptotes, where it's the line that it'll never touch. And that's our lesson for today.